All right, so let's continue on with this problem. So the next part asks, what is the time when it is 1 meters above, when the ball is 1 meters above the clown's hand and falling downward? So this is related to the previous question. So we are looking for our time. We know that we're dealing with a acceleration of 9.81 meters per second squared. This is downwards, and we've been saying all along that this is going to be negative. The question is looking for, we also know that we have an initial velocity of 10.0 meters per second, and this is upwards, and we've been saying that this is positive. And I know I said we're going to try to avoid using calculated values, but in this section we can't. Okay, we do have to use the velocity that we solved for in the previous question. So this is approximately 8.97 meters per second. And this is specifically when the ball is going downwards. So this value is going to be negative. So now that we know that, and that was the hard part there, okay, we can solve for t, which is a simple matter of using our change in velocity over change in time. And we just have to be sure that when we're doing this calculation, that this is our full calculator value and not what we actually wrote down over here. So let's plug in our values. So we have, I'm going to jump down over here, negative 9.81 meters per second squared is equal to negative 8.97 meters per second minus positive 10.0 meters per second, and we're looking for our time. So I'm just going to go ahead and calculate this quickly. Okay, and then if you go ahead and did that calculation, we should be getting 1.93 seconds as our time. And again, just gotta put it through the common sense filter. We said that it takes 1.02 seconds to reach maximum height. So it seems to me that 1.93 seconds is reasonable because that's going to be after it reaches maximum height and when it's falling, and also moreover, it's close to the ground, right? So that totally makes sense. All right, so let's go ahead and look at the last part of this example. Okay, we're asked for this entire trip, a position time, velocity time, and acceleration time graph of this projectile. So we'll say that this is our position time graph, this is our velocity time graph, and this is our acceleration time graph. And we'll say that up is positive, down is negative. So if you're not sure how to do this, or it's not really clear, I would pause the video right here and just try to think to yourself what these graphs would look like. So I'm going to start with the acceleration graph because I think this one is the easiest. So we know that this object throughout its entire trip is going to be dealing with a constant acceleration. And this acceleration is acceleration due to gravity, which is 9.81 meters per second downwards. So if I had to sketch this out, I would show a line demonstrating that this acceleration is constant through the entire trip, and you can see that it's actually in our negative axes. So I'm not asked to put a number here, but if I had to, okay, we would know that this number is 9.81 meters per second squared. Okay, so it doesn't matter if the ball is going up or if it's going down, okay, the acceleration is going to be the same. Okay, so the second graph, which I think it's a little bit easier, or a little bit harder, but not the hardest, is the position time graph. So how do we sort this out? Okay, well, we know that at time 0, we are at our origin. And we know that when the ball hits the hand after it has been thrown up into the air, it's going to be at the origin at the end of the trip. And we know that halfway through this trip, the ball is going to reach a maximum height. So Now you might be thinking, well, I should just connect the three dots with straight lines, but we can't do that, right? Because we're not actually dealing with constant uniform motion, right? We're dealing with accelerated motion, or uniform accelerated motion. So on the way up, our velocity should be decreasing due to gravity, and then on the way down, our velocity should be increasing. So if you remember that velocity is equal to the slope of our position time graph, our slope should be getting less steep as we go up, be 0 at the very top, and then get steeper and steeper and steeper on the way down. And I know that's not a perfect diagram, but I did my best. That's all that counts. Okay, so that's what my position time graph looks like. Okay, so if we go over to our velocity time graph, how do we sort this out? Okay, well, we know that at the beginning we have positive velocity. So in fact, if we had to write a number in here, this would be 10, right? Because it's 10 meters per second up. We know that velocity is going to decrease to 0 at the peak, and that happens at the halfway point. And then what happens after that is maybe a little bit tricky to think about, right? Because our velocity does increase as it goes from maximum height back towards the ground, but it's increasing in the negative direction, right? So we have a decreasing velocity to our maximum height, and then an increasing velocity, but in the negative direction, or in other words, downwards. So again, if I had to put a number here at the very end, okay, this would be -10, right, below the origin. And then this slope, you can see it's negative. And of course, the slope of our VT graph is going to be equal to our acceleration. And our acceleration, as you can see from the graph right beside it, is also negative. All right, so that answers all the questions from this section. You guys can go ahead and work on the assignment